Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're looking at optimization, and we're doing it using approximated derivatives. In a previous lesson, we had talked about how to do approximate differentiation, okay? And we have lots of formulas for that. We want to pair that with what we know from calculus, that we can find the maximum or minimum value of a function by taking the first derivative and setting it equal to 0. But sometimes taking the derivative is just hard, or you're not certain it's difficult enough that you're not sure you would do it reliably, or maybe you couldn't solve for where it's equal to 0 anyway. It provides an equation that's not analytic. So we can do that using our approximate derivative functions. So we want to use the best possible, okay? That's going to get us to our answer fastest. And so that is the central difference using two terms on either side of our point, okay? So if we're going to do this, what we want to do is, well, let's talk about the problem that we looked at in the previous video. So finding the maximum profit, okay, for a given flow rate. So P is 7.3 m minus 0.025 m squared, and we want to find out what flow rate will make this profit be a maximum. Okay. And if we want to do this using this technique, not analytically taking the derivative, although yes, we know this one is easy, but what I recommend doing is just start by setting up a column of x values that are all separated by value delta x, right? We need delta x for our formula. And then evaluate the function at each one of those. Now, because we're using the higher order central difference formula, we are going to use that to evaluate the first derivative at every point, but we won't be able to do the first 2 points or the last 2 points. Okay, so start it early enough, stop it late enough that that's not going to impact your ability to understand your answer. And then scan the list, see where you have a sign change, and then you can use that to modify your starting value of x and your starting delta x, and just keep repeating this until you get to an answer. So I have this one set up already in Excel. I'm not doing this in VBA, I am only doing this in Excel. So I started with a first value of x of 0. I knew I wanted something positive. My delta x I have set over here, and I'm going to count by 5s. Again, I happen to know that the answer is going to be 146, right? So, account for that. Whatever range of values you know is possible for your function, work with that. And then I evaluated the function by pointing to that cell. Now when I came down to this one, notice that I'm using the cell above and adding delta x. And I've copied this formula all the way down. As a reminder, I'm using the dollar signs. I got that by using the F4 key. And that way it's going to always add the delta x value here. I've copied the function down, and then I've put in my formula for the derivative, the central difference formula. And it's pointing to the delta x value, and then the 2 points before and the 2 points after with the correct formula. Okay, so if I do that, and you can scan down through here, right, until you see a sign change. There you go, 145 to 150. Exactly where I expected it to be. And so what I can do is now come in and say, okay, 145, and I'll change delta x to 0.1. Okay, and scan down, and 146 has, well, this has negative 6.6 times 10 to the minus 13. Remember, there's always round off error there, so when you get down to those T9C numbers like this, that's essentially 0. And so we actually have our answer. If you weren't sure, you could start at 145.9. That should be a 145.9. And maybe I want to count by 0.01 this time. And yes, indeed, it does seem that this is my answer. And you can continue doing this until you get it refined to however many digits you're looking for in your answer. Okay, so not terribly difficult to do. Let's do this for another example. Something a new problem, okay? In this case, another example from chemical engineering is that phase equilibrium problems really are minimizing the value of the Gibbs energy, okay? And so for a binary mixture, we can write it in terms of a single variable x, the composition of component 1, because remember that the composition of component 2 is always 1 minus x. And I know my answer needs to be between 0 and 1. Okay? So here is the Gibbs energy function in this particular case. And let's look at that. So negative log of 4 plus 216x squared minus 216x cubed. I want to evaluate this between 0 and 1. I'm going to use the same spreadsheet. So I'll start at 0, and this is negative log of 4 plus 216 times x squared minus 216 times x cubed. Okay, that looks right. And, oh, I wanted negative of that. All right, there we go. And I'll just copy this down. Okay, and I'll count this by, I'll start with a count of 0.1 for my delta x. And so I don't need any values greater than 1. And what I see is that it looks like it's between 0.6 and 0.7. So I'll put in 0.6 and count by 0.01. Okay. And so it looks like it's between 0.66 and 0.67. 0.66 is my start, and I'll count by 0.001. And again, it looks like it's right in this range here. So I'll just keep modifying my first number and adding, another 0 there for the digit. And it really looks like it's honing in on 2/3. You could continue this to verify it for yourself, but indeed the correct answer would be at 2/3. So composition of component 1 is 2/3 and 1/3 is component 2. Now this concludes our examples for this particular technique. It's, we're not programming this in, but it is fairly simple and easy to apply. Thank you very much for your time. And in the next lesson, we will look at a little bit more haphazard trial and error method that Excel will do for us. Thank you very much for your time.